For as long as human beings have been around, we've been counting things, and we've been looking for ways to keep track and represent the things that we counted. So for example, if you were an early human and you were trying to keep track of the days since it last rained, you might say, okay, let's see, it didn't rain today, so it's one day has gone by. And we now use the word one, but they might have not used it back then. Now another day goes by. Then another day goes by, then another day goes by, another day goes by, another day goes by, another day goes by, and then it rained. And so when his friend comes and says, well, how long has it been since we last rained? Well, you would say, well, this is how many days it's been. And your friend would say, okay, I think I have a general sense of that. And at some point, they probably realized that it's useful to have names for these. So they would we call this 1, 2, 3, 4, 5, 6, 7. And obviously, every language in the world has different names for these. And I'm sure there are lost languages that had other names for them. But very quickly, you start to realize that this is a pretty bulky way of representing numbers. One, it takes a long time to write down. It takes up a lot of space. And then later, if someone wants to read the number, they have to sit here and count. And it's hard enough with 7, but you could imagine if there were what we call 27 of it or 1,000 of it. Then it would take up possibly a whole page. And even when you count it, you might make mistakes. And to solve this, human beings have invented number systems. And it's something that we take for granted. You might say, well, isn't that just the way you've always counted? But hopefully over the course of this video, you'll start to appreciate the beauty of a number system and to realize that our number system isn't the only number system that is around. The number system that most of us are familiar with is the base 10 number system, often called the decimal number system. And why 10? Well, probably because we have 10 fingers, or most of us have 10 fingers. And so it was very natural to think in terms of bundles of 10, or to have 10 symbols. So however many bundles you have, you can use maybe your fingers and eventually your symbols to think about how many there are. And since we needed 10 symbols, we came up with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These 10 digits, these are our 10 symbols that we use in the base 10 system. And to just give us a little bit of a reminder of how we use them, imagine the number 231. So 231. What does this represent? Well, what's neat about number systems is we have place value. This place all the way to the right, this is the ones place. This is the ones place. This literally means 1, 1. One bundle of 1. So this is 1, 1 right over here. This right over here, this is in the tens place. This is in the tens place. This 3 here literally means 3 tens. So this literally means 3 tens. And this 2 here is in the hundreds place. It's in the hundreds place. Hundreds place. And so this represents 2 hundreds. 2 hundreds. And you add them together. And once again, I'm still thinking in base 10, you'd get 231. This is 2 hundreds plus 3 tens plus 3 tens plus 1. And in our base 10 system, notice, every time we move to the left, we're thinking in bundles of 10 of the space to the right. So this is the ones place. You multiply by 10, you go to the tens place. You want to go to the next place, you multiply by 10 again. You get the hundreds place. If you're familiar with exponents, 1 is the same thing as 10 to the 0 power. 10 is the same thing. 10 is the same thing as 10 to the first power. So this is the tens place, 3 tens. And 100 is the same thing as 10 to the second power. And obviously, we could keep going on and on and on and on. That is the power of the base 10 system. So you might be curious now. Well, what if this wasn't a 10 here? What if we did, well, let's just go as simple as we can. You can almost view this as a base 1 system. You only have one symbol right over here. But what if we went to something slightly more complex, a base 2 system? And you'd be happy to know that not only can we do this, But the base 2 system, often called the binary system, this is called the decimal system, often called the base 2 system, often called the binary system, is the basis of all modern computing. The underlying mathematics and operations that computers perform are based on binary. And in binary, you have two symbols. You have 0 and you have 1. And the reason why this is useful for computation is because all of the hardware that we use to make our modern computers, all of the transistors and the logic gates, they either result in an on or an off state, an on or an off state. And so what we do is, when you use your calculator or whatever, you might be operating in base 10, but underlying everything, it is doing the operations in binary. But you might say, well, how do we actually think in terms of binary? Well, we can construct similar places here, but instead of them being powers of 10, they're going to be powers of 2. So let's set up some places here. So all the way on the right, 2 to the 0 power is still 1, so we could still call that the 1's place. Then we can move to the left of that. We can move to the left of that. That would be 2 to the 1st power, so we could call that the 2's place, and I could even write it out if I want. 2's place instead of the 10's place. Then I could keep going. Instead of this space being the 10 to the 2nd or the 100's place, it'll be the 2 to the 2nd or the 4's place. And I can keep going. This, and I encourage you actually, pause the video and try to build this out for yourself. What would this be? Well, this would be 2 to the 3rd or the 8's place. And notice, every time we're doing this, we're multiplying by 2 every time we go to the left, just like we multiplied by 10 here. So notice, everywhere you see these 10s, we're now dealing with 2's. Let's keep going. Let's keep going, and then we can actually represent this number using binary. So let's do that. So this right over here, I've already used that color. This right over here, this is 2 to the 4th. We could call that the 16's place. And then we could have, I'll reuse some of these colors. This is 2 to the 5th. We could call this the 32's place. Then we can go 2 to the 6th. 2 to the 6th. We could call that, well, we're multiplied by 2 again, or 2 to the 6th is 64. So this is 64's place. It tells us how many 64's. Do we have a 0 or 1 64's? And we'll see that in a second. And then we can go over here. This would be 2 to the 7th. That would be the 128's place. 128's place. And we could obviously keep going on and on and on, but this should be enough for me to represent this number. And in future videos, I will show you how to do that. But let's actually represent the number. It turns out that this number in decimal can be represented as 1, 1, 1, 0, 0, 0, 1, 1, 1, let me do that in yellow, 1, 1, 1 in binary. And so what does this mean? This means you have 128 plus 164 plus 132 plus no 16s plus no 8s plus no 4s, plus 1 4s plus 1 2 plus 1 1. And so you can see that these are going to be the same thing. Notice, this is 128. So it's 128 plus 64 plus 64 plus 32 plus 32. Well, we have 0 16s, 0 8s, so we're not going to add those, plus 4, 1 4, plus 1 2, plus 1 2, plus 1 1, plus 1 1. And add these together. And once again, when we're doing this, when I'm writing it this way, I'm kind of using the number system that we're most familiar with, that we're most used to doing the operations in. But when you do it, you will see that this is the exact same number as 231, that this is just another representation. One isn't better than the other. The only reason why I converted to this is what I'm just used to thinking in. It's what I'm used to doing operations in. So hopefully you find that pretty interesting. This, to me, this was kind of opened my mind to the power of even our decimal system. In future videos, we'll explore other number systems. And the most used ones, base 10 is obviously is used very heavily, binary, and there's also hexadecimal, where you don't have 2 digits or not 10 digits, but you have 16 digits. And we'll explore those in future videos and how to convert between or rewrite the different representations in different bases.